Hi, in this video we are going to look at number patterns for grade 12. Number patterns for grade 12. So one thing we need to just state it and or get it out of the way is that we are supposed to know all the three types of number patterns that we deal with at high school level. I don't know if those who proceeded with these number patterns, they had to do with any other type of number pattern. But yeah, these are the types of number patterns that we need to deal with. Linear, quadratic, as well as geometric. So we're going to look at the three and then see what the difference is between the three. So I'm just going to use a table like that. We have linear, and then we have quadratic, let me get the spelling right, I can't just be writing things in here. And then we have geometric. So I'll just try to summarize the difference between the three types of number patterns in this video. So the main difference obviously is the general formula for each. Tn equals to dn plus c, or Tn, because this one has two types of formulas that you could use for it. I'm trying to write Tn equals to a plus n minus 1 times d. That's the second formula. However, for quadratic, the formula is Tn equals to an squared plus bn plus c. There's only one type of a formula there. For geometric, the general formula is given by this: ar exponent n minus 1. That would be the first difference. And one thing that we need to look at is that for here in linear, we have a common difference. We have a common difference, and then in quadratic number patterns, we have a second common difference. And then for geometric number patterns, we have a common ratio. That common ratio for geometric number patterns is given by this r. This r represents the common ratio. In linear number patterns, the d represents the common difference. In what you call quadratic number patterns, the common difference is represented by 2a, not just a. And then for linear number patterns, a represents the first term. That is a equals to t1, because t1 is the first term. And for quadratic number patterns, a plus b plus c, they represent the first term, which is term 1. That they give you the value of the first term pretty much. And then 3a plus b, it gives you the value of what? Of this first difference, pretty much the value of the first difference, which is basically the value of t2 minus t1. And then I already said the second difference is actually 2a. And then in geometric number patterns, a equals to t1, r equals to the common ratio. Moving on, one other thing that I would like to mention regarding these three types of number patterns is that we'll do examples. I'm just trying to give you the difference between the three at this point. The examples, we are going to do them in another video. Here I'm just trying to give the difference. Okay, moving on, we have a formula to calculate the sum, or they call it the sum formula or the series formula. For arithmetic sequences, it's given by this: sum of n equals to n over 2 into a plus l. Or we also have the other one, which is Sn equals to n over 2 k what is it? It's 2a. These formulas are even usually given to you, or always given to you in your formula sheet or question paper. This is 2a, so you can always refer there to make sure that you get them right. However, for this video we are looking at the difference between the three, so we are definitely going to look at them from here. Here there's no formula for sum to n, or sum of n, or the series formula, or the sum formula, whichever way you prefer to call it. It's fine, as long as you know what you mean by what you say and you know how to apply it. You might be able to get away with it. And then for geometric number patterns or sequences or series, you have this formula to calculate the sum of the numbers in a sequence. This is the formula. You also have the other formula. You just need to pick the one that you feel like it makes better sense to you. But these two formulas, they pretty much both work the same way. However, this last one is the sum to infinity. These first two that I stated, they are for a finite sequence. This last one is for an infinite sequence. By infinity, you know, they will put the first terms and then they use these three dots at the end to show that this series or sequence continues to infinity. Then you know you have to use this formula. When you are busy using the formulas, just make sure that your r is between, because these formulas are only going to work out if your r is between 1 and -1. I mean, the infinity one, it only converges if r is between -1 and 1. The ones which only work for under certain condition are these first two. They are only valid, or you are only going to get any answer which is not undefined if r is not equals to 1. Because if r is equals to 1, the denominator is going to give you 0. Just look out for that, but you will see as we start doing examples. And then what else are we looking at in terms of the difference between the three? We look at the fact that for this quadratic number patterns, the first difference, when you get the differences for, you have let's say you have term 1, you have term 2, you have term 3, you have term 4. As you get the differences like that, you get to have a new sequence. That sequence, it's basically a linear number pattern. So just remember that, and then you should be fine. And then to find the maximum or minimum term, you can only do that in a quadratic number pattern. And how you do that is by saying n equals to minus b over 2a. That's when you're trying to find the position of the minimum or the maximum term. So also, we basically use the turning point equation. If you remember from grade 10, this equation is basically for the turning point of a parabola, because basically quadratic equation is the equation of a parabola, the same thing. So remember, this is the parabola. It could either be like that or like this. That's the shape. And then for linear, it's always a straight line. It could be like that or like that or like that or like that. Could be horizontal or vertical, slanted to the left or slanted to the right, depending on the conditions. And then for geometric is basically an exponential function. Remember, the graph is something like that. It could be like that, or could be facing down, inverted like that, or like that. But it's basically an exponential graph. That's a geometric function. It represents an exponential graph. So I think, having stated all these things, or let me just add even the formulas. Remember the formula you're used to for number patterns which are linear. It's basically y equals to mx plus c. This is similar to this equation, if you remember. The first equation actually of linear number patterns. So that equation is still valid. And then for quadratic or parabolas, we have the equation ax squared plus bx plus c. That's the formula you're used to. You should be used to at least. And then for what you call exponential or geometric, the formula that you should be used to by now, it's this one. If you look at the formulas that I've just given, they look very much similar to the general formulas of each type of a number pattern. So just remember that. And then we will do examples so that you get to understand the application of each type of a formula. Then you should be fine. I don't see us having any problem at any point. One other thing I wanted to do is to also talk about sigma notation. When we represent a number pattern or a series in sigma notation, we are just basically using the symbol for sigma, putting the general equation there, and then indicating that this equation is starting from when n equals to whatever number and until it ends at whatever number we say. But that is whatever value, if you were to evaluate this, it's just going to be equals to the Sn, because the sigma just basically means the sum. For quadratic number patterns, for grade 12, there's no need for you to learn how to sum the patterns or the terms of a quadratic number pattern. For geometric, however, it's essential that you learn that. So the same way you have done when you were doing linear number patterns, when you represent those the terms or the pattern in sigma notation, you will still do this until you get to the last term, which usually I would use t. My reason for using t is as follows. Okay, let me not continue with that line, because now I want to get to the definitions of some of the things. My reason for using t and b is because in my mind, b is for bottom, t is for top. So by that, to make it make sense, I'm saying to you that to calculate n, this n, because when you are summing values or terms of a sequence or a pattern, you need to know how many of them you are adding together, because the n here, this n, it stands for how many terms you are adding together. Yeah. However, the n here in the general equation, it stands for the position of a term. Position of each term. For instance, term 1, because it's in position 1, n it's 1. However, in this equation, you need to get n in a slightly different way, not the same way you would get n in those equations, right? So just keep that one in mind. Remember, this is the last term, and then a is still the first term. It has already been described there, so it's still a, it didn't change. And then, assuming that all that is clear, you should be fine. But remember, this n in a Sn equation, it's basically equals to top minus bottom plus 1. That's the equation you get n in the sum of n equation. That's why I use t for top, b for bottom, plus 1. That's how you will calculate your n, because how you analyze the n, it's actually saying indicate how many terms you are adding, so that's how you get the number of terms that this equation, either for arithmetic or geometric, it's adding. So just be clear about that and you should be fine. If there's anything that I'm leaving, I think we'll just cover that one when we are doing examples, but I think I've tried to cover everything. From here, we just do examples and keep it moving. If you have any question, you just ask, then we keep it going.